Hello everybody, I've got another physics video here today, and today we're going to be covering the right-hand rule. And the way that we're going to do this is I'm going to show us a problem, and then I'm going to show myself using the right-hand rule to solve that problem, and then we'll go back and actually find the right answer. So this first one, we have a charged particle with charge q and mass m. It's moving with a velocity v, perpendicular to a uniform magnetic field. The magnetic field is directed into the page. Which of the following statements is true about the motion of the particle? So let's see the right-hand rule in action. So for the right-hand rule, there are two ways that you can do it. You can use your three fingers like this to represent the three vectors, or you can use your hand and your thumb and curl your hand in the direction of the vector. And I'm going to show you both methods. So for this, it says that the magnetic field is into the page. So the first thing I'm going to do is I'm going to say, okay, my middle finger in this case is the magnetic field. So it points into the page here. Your pointer finger is the velocity of the charge in the opposite, or in the perpendicular direction. So it is like this, middle finger into the page, pointer finger like this, and your thumb points to the left. If you were to do this with your hand curled, you would have, here is your velocity, you curl your hand in the direction of the magnetic field, and then your thumb still points to the left. Now what's going to happen is that thumb is the force vector. So it is going to push on the charged particle that has a velocity in this direction and going to push it to the left. So that's going to cause it to go to the left like this, and then it's going to keep pushing on that. The magnetic field doesn't change, and it's going to go in a circle with uniform radius. So having seen the right-hand rule now, we know that it's going to move in a circular path. The only one that satisfies this is this first answer here. But where does that term R equals mv over qb come from? Well, let's find out. If we use the Lorentz law, we know that F equals q, which is the charge of the proton, times the velocity vector v, crossed with the magnetic field vector b. And it's important to realize that this x in the middle here is a cross product, not multiplication. This can be rewritten as F equals QVB sine of theta, with theta being the angle between the velocity vector and the magnetic field vector. In our case, they're perpendicular, it says so here, so theta is 90 degrees, and sine of 90 degrees is 1. So F is just QVB. Now we know from how I showed you that the particle is going to move that it moves in a circular motion with the force constantly directed inward. If you think back to kinematics, this lines up very well with the centripetal force, which has the equation force of centripetal equals mv squared over r. So we can actually set these two equal to each other and just say mv squared over r equals qvb. We want r by itself, so you multiply both sides by r and then divide the right side by qvb, and we end up with mv squared over qvb equals r. This v and this v cancel out, so we have mv over qb equals r, which you see does match up with the first option there. Okay, for this next problem, we have a proton with charge q and velocity v. It enters a uniform magnetic field at an angle theta with respect to the field direction. And then it asks which expression correctly describes the magnitude of the magnetic force acting on the proton. We kind of already solved this previously, but I'd like to draw it out and explain it further. So let's say we have a magnetic field pointing downwards. So here's our magnetic field vector B. And then let's say, I want to use red, we have a proton entering from the top right here. It has an angle theta here with that uniform magnetic field. You can see if we were to continue the magnetic field, there's the vector there. So that theta is what governs the force. So we have F equals QV crossed with B, or F equals QV, this is a vector, B sine theta. And that is this first option right there. So now we have a positively charged particle moving to the right, and it experiences an upward force. And then it gives us a diagram. So let's see the right-hand rule in action here. So with our right-hand rule using either method, let's use the palm method first. So the palm method, your thumb is the force vector, your fingers point in the direction of the charge or the current, and then they curl in the direction of the magnetic field. So you can see that that is into the page. And then if you were to use this method where you have your 3 fingers, your thumb is your force vector, your index finger is the current, and so with the current pointed to the right, the thumb pointing up, you can see that the middle finger, which is the magnetic field, points into the page. Okay, so now that you've seen the right-hand rule, it is pretty obvious that it is directly into the page. Okay, now we have a long straight wire carrying a steady current I, and then it asks us to identify which statement correctly describes the magnetic field generated by the wire at a distance r from it. To use this, we need the equation for a to solve this, we need the equation for a magnetic field at a distance r, which is given by B equals mu naught, which is the permeability constant, times I, which is the current, over 2 pi r, which is the radius. If you were to ignore all of this, you would see that B equals all of that stuff, so I'm just going to draw some parentheses, times 1 over r. So we see that B is inversely proportional to r. The only one that satisfies that is option 3 here, so we know this is correct, but it also says that the magnetic field forms concentric circles around the wire. And I'd like to show you how that happens. So let's say that this is our wire extending off to infinity here. So this is our long straight wire. The magnetic field is going to go in circles like this around it. And let's say we're concerned at what's happening over here at this radius r. It's going to be this circle all the way around wherever you are with regards to the wire there. So we see that they form circles that are concentric, which means that they're centered around the wire. So now we have a proton moving perpendicular to a uniform magnetic field. Which of the following best describes the path of the proton? So if you recall my first example with the right-hand rule, we can say that, let's say that the direction of the proton is up. So this is our velocity vector. And let's say that our magnetic field is moving into the page. This means our force vector is moving to the left. I showed this earlier in the video, and you can go back and look at that if you need a little refresher. So the force vector is going to push to the left. It's going to change the direction of the velocity of the proton. So it's now going to look like this, with this being velocity, this being the force, and magnetic field here still being into the page. And then it's going to push it to the left again. So velocity is now doing something like this. Magnetic field is into the page still, and the force vector is still perpendicular there. And this is going to happen as it goes all the way around the circle. What does not happen, though, is that the force vector doesn't actually change it doesn't change the speed, it just changes the velocity. I like to imagine that it's just pushing on the velocity vector and causing it to change the angle rather than actually influencing the speed at all. And the reason for this is because it doesn't actually point. Since it's a perfect 90-degree angle here, it has the force in the x direction and the velocity in the y direction. And so it doesn't actually contribute to that velocity whatsoever. It just changes the direction. So it moves in a circular path with a constant speed. So with this problem, we have a straight current carrying wire. It's placed in a uniform magnetic field. The current is flowing to the right. So we have this as our I, and the magnetic field directed into the page. What is the direction of the force exerted on the wire by the magnetic field? So let's see the right-hand rule in action. So using the palm method first, we have the current directed to the right. That's these fingers this way. We have the magnetic field into the page, so pointing this way. And then we have the force vector pointing this way. If you were to use this method instead, we first have the current pointing to the right, the magnetic field then pointing into the page, that's the middle finger here, and then the force points upwards. You can see you can use either method interchangeably. It's really just whichever you prefer. Some people have a difficult time doing this. I'm having a really difficult time trying to show you this, so I much prefer this method. So going to answer the question, we saw that the direction of the force exerted on by the wire by the magnetic field is upward. So now we have an electron moving with a speed of 5 times 10 to the 4th meters per second. So this is our velocity vector. It is perpendicular to a uniform magnetic field of magnitude 0.2 teslas. And then it is asking the magnitude of the magnetic force on the electron. So if we use our equation, F equals QV cross B, then that becomes F equals QV B sine theta. We see that it is perpendicular, so sine of theta is sine of 90, which is just 1. So we have F equals QVB. Conveniently, we've already been given the charge of the proton, that's just E. So this becomes Q, which is 1.6 times 10 to the negative 19 coulombs, times the velocity vector, which is 5 times 10 to the 4th meters per second. And then finally times the magnetic field, which is 0.2 teslas. And then if you were to calculate this out, I already did it on a calculator ahead of time, you would get that the force is equal to 1.6 times 10 to the negative 15 newtons, which is this first option. So this is the last problem we're gonna do here. We have a proton traveling at a speed of 5 times 10 to the 7 meters per second. It is through a 1 Tesla magnetic field. What is the magnitude of the magnetic force on the proton if the angle between the proton's velocity and the magnetic field vector is 30 degrees? So what this looks like is, let's say we again have our magnetic field pointing straight downwards. Then we have our proton traveling through the magnetic field. And if we want that angle to be about 30 degrees, that would be about right there. So this is our theta, which is our 30-degree angle. So we can then use the Lorentz law again. Remember, we have F equals QV B sine of theta. So this is F equals Q, which is the charge of the proton. So that's 1.6 times 10 to the negative 19 coulombs times the velocity vector, which is 5 times 10 to the 7 meters per second. And then times 1 Tesla, that's convenient. And then times, finally, we have the sine of 30. And again, I already calculated this ahead of time, but if you were to plug this into the calculator, you would get 4 times 10 to the negative 12 newtons as your final answer.